Okay, I want to do just a couple more problems just by way of a review. These are some of the things we did early in the second half of the course, and just give you one more example of each. The first one is a related rate problem. Again, it's one of my favorites. Suppose you've got yourself a big Ferris wheel, and the radius of this Ferris wheel is 25 feet. Okay, and it's going around in this direction. And you want to know how fast are you rising when you happen to be 15 feet above the center of the Ferris wheel, which is right there. So how fast are you rising when 15 feet above the center? Okay, how fast are you going up? Okay, so remember how to do these. The first one is what do you want? And in this case, what we want is how the height is changing. So we want dh dt, and we want it at a particular time. We want it when h is 15, and by saying h is 15, I'm taking all these distances to be relative to the center of the Ferris wheel. Okay? Oh, by the way, I forgot to say that the Ferris wheel is going 3 revolutions per minute. Okay? So that's how fast the Ferris wheel is going around. It's going around 3 per minute, which I think is kind of fast, but we'll assume that for sake of this example. Okay, so that's what we want. What do we know? And I just told you, what we know is that this is how fast it's going around. So the hard part of this problem is putting that in terms of something which is going to be useful. It's 3 revolutions per minute. This angle is going to become important. Let that be theta. And so how fast is theta changing? What is d theta dt? What is d theta dt? Well, it's going 3 revolutions per minute. Each revolution is 2 pi, so it's actually going 6 pi radians per minute. Agreed? So that's the hardest part of this, is just taking this and seeing it's this. Okay, third thing then is to find a relationship between h and theta, and hopefully this kind of presents itself to you. H over 25 is going to be the sine of theta. So if h over 25 is the sine of theta, that means that h of t is going to be 25 times the sine of theta of t. Okay, so there you go. Now it becomes kind of routine. Take the derivative. And so we're going to get dh dt is equal to 25. The derivative of the sine of anything is the cosine of that thing, times the derivative of the inside. T is your variable, so this is theta of t. So the derivative of this is d theta dt. There you go. And now your fifth step is we want to find what's dh dt at what point? When h is equal to 15. So it's going to be 25 cosine of theta. Well, look at here. If this is 15 and this is 25, then this is a 3, 4, 5 triangle. You can use Pythagorean's theorem and get that if this is this thing squared minus this thing squared, take the square root of it, and you're going to get 20 here. In particular, 20 squared is 400, 15 squared is 225. You add those together, you get 625, which is 25 squared. So given that this is 15, this is 20, and so the cosine of the angle is going to be 20 over 25, which is the same as 4/5. So you just have 4/5 there, and then d theta dt is 6 pi. So that's all there is to it. And so that's going to be, cancel this with this, and you get 5. 5 times 4 is 20. 20 times 6 is 120 pi. And I guess the units would be, this is feet, so it's going to be feet per minute. So if you want to, go ahead and calculate that and see once how fast you're rising. I think you're going at a fairly good clip, like 4 miles an hour or something like that, if I remember this problem. But anyway, there it is right there. Okay, so kind of a nice one. Okay, so that's the related rate. I'm not going to finish the max-min problem I give you. I'm going to let you do it on your own, but I'm going to give you what the answer is. It's a really nice problem. It's another one that you see parts of this in the book, but I kind of tied them together. Okay, here's a classic problem. Find the minimum amount of a metal. Let's say a minimum area. Let's say the minimum area of metal to form a cylindrical tin can with volume V. Okay, so in other words, you're making tin cans for Campbell's soup or tuna fish or whatever else, and you want the volume of this can to have V. Okay, that's what the volume is. And so given the fact that the volume is V, you want to do it as economically as possible. You want to do it with the minimum possible surface area. And of course the surface area is going to be both the top and the bottom and along the side. So that's what you're doing. So if we were to do this problem, let's just think how we would start. In this case, you want to minimize the area. And the area, let's let this be H. And let's let this be R. And so the area is going to be, here's the area right there. It's going to be pi r squared plus pi r squared is going to be 2 pi r squared. That's the top and the bottom. And then the area along the side is going to be 2 pi r. That's the distance around the bottom. And if you multiply that by h, you get the sides. So that's the minimum area right there. And then, so that's what you want to minimize. And then your constraint, the thing that keeps that from being as small as you want it to be, is that you have to have a volume of V inside. So V is a constant. It's some particular number. If it helps you out, just make it 7 or something, but that's a constant. And so the constraint is what's the volume of a tin can? It's the area of the base, pi r squared times h. That's got to be equal to V. So do you remember how you finish it? You solve this for one of them and you stick them in here and you differentiate. Okay, I'm not going to go any further with that. I'm going to give you another problem which is kind of the complement of this one. And that is, find the largest volume cylindrical can made with a surface area. Okay, so notice this sounds very similar, but here, what was happening here? Here, we were told what the volume was, and given that what the volume was, we wanted to get the minimum surface area. Here, we're told what the surface area is. The surface area is A, and we want to get the largest volume. So it seems very similar, okay? So here, you're still making the tin cans. You're still trying to do it as efficiently as possible. But here, instead of being told what the volume is, you're told, oh, for every tin can, the total area you have for the tin can is A. And given that the total area is A, you want to maximize the volume. So here, the first step would be to maximize the volume And so here you'd write volume is equal to pi r squared h. And now in the second step, you say, what's the constraint? This is the constraint. The constraint is that 2 pi r squared, there's the top and the bottom, plus 2 pi r h, there's the side, that's got to be equal to a. And a now is a constant. That's the constant. This is your variable. So I'm going to let you leave it to you, the viewer, to see once if you can solve both of these problems. And you might expect that since they're both trying to do the same thing, they're both trying to get as much volume per surface area as possible, that the shape of the two cans should be the same. And in fact, you're right. And I'll tell you what the shape is. Here's the final answer. The shape is that the height is equal to twice the radius. There's your final answer, which means the height is equal to the diameter, which means if you were to look at this can from the side, it would look like a square. This and this would be the same size. There's the way to both maximize the volume, or that's the way to minimize the surface area. Okay, so try them both. They both involve a bunch of algebra, but see if you can do them. A great problem. Okay. Okay, and then the very last one I want to do, I think I still have a couple more I kind of want, is a graphing problem. And we've done one similar to this, but let's look at this one. F of x is equal to x squared e to the negative x. Just another nice graphing problem. I'm going to go to a black marker here. And let's go through the steps of it. This is a nice one. And again, go ahead and pause the video and see if you can do this on your own. The domain is everything. Intercepts. There's just one intercept at 0, 0, because that's the only place where the function is equal to 0, and when you stick in 0 for x, you get 0. Symmetries, none. You put in a negative x for x there. You're going to get negative x quantity squared times e to the negative of negative x. That becomes x squared e to the x. It's not the same as the original, nor is it the opposite of the original. So the negative of the original. So no symmetries. Asymptotes, vertical, none, because there's no places where the denominator goes to 0. Horizontal, well, let's see. What's the limit of x squared e to the negative x as x goes to infinity? Remember how to do this one? You can write it as x squared over e to the x. Now you have infinity over infinity. And you use L'Hopital's rule on it. And you're going to get 2x over e to the x. It's still infinity over infinity. So you use L'Hopital's rule on it yet again. And when you get here, you get 2 over e to the x, and that goes to 0. So, so the limit of the function as x goes to infinity is equal to 0. What happens as you go to minus infinity? As you go to minus infinity, you can again write this as the limit of x squared over e to the x as x goes to minus infinity. And as you do, the top is going to be getting larger and larger. You take a big negative number and square it, you're going to be getting a huge positive number. The bottom, as x goes to negative infinity, e to the x, what does it do? It goes to 0. So this thing is approaching 0. It'll be positive. What happens is you take a big number and divide it by a small number, you get a really big number. So let's go ahead and write that down just to have that information. going off to infinity. Okay, very good. Again, stop the video as needed. I'm doing this a little faster because I want to get a lot done here in this last lesson. But take time and do it. Now, let's go ahead and do increasing, decreasing. Increasing, decreasing. So, what do? We take the derivative. And we're going to get the derivative of the first times the second plus the first times the derivative of the second. The derivative of the second is going to be a negative e to the negative x. Now you can factor a x e to the negative x out of both, and you're left with 2 minus x. So if you look at that and say, where will that be 0? That'll be 0 both at 0 and at 2. This will always be positive. So you put in a number greater than 2. This is going to be negative, positive, positive. So the whole thing is going to be negative. Put in a 1 here. Everything's positive. Put in a negative 1. And it's going to be what? Negative 1. This is going to be positive. Positive and negative. So this is the first derivative we're talking about. So it's decreasing, increasing, and decreasing. Okay, a nice problem. Okay, let's do the same thing with concavity. Take the second derivative. Okay, let's use this form right here for the second derivative. Take the derivative of the first times the second plus the first times the derivative of the second, which is going to give me a negative e to the negative x. Same thing here. Take the derivative of the first, negative 2x, times the second, plus the first, which is going to be a negative x squared, times the derivative of the second. The derivative of the second, the negative comes out again and makes that a positive e to the negative x. So look at here, I can factor an e to the negative x out, and I'm left with x squared minus 4x plus 2 is equal to 0. So I want to know, when will that be 0? This will never be 0. I need to use a quadratic formula to find out when this will be 0. So x is going to be 0 when? At 4 plus or minus the square root of negative 4 squared is 16. Minus 4 times 1 times 2, which is minus 8, all over 2 times 1, which is 2. And so 4 into 2 is 2. The square root of 8 is 2 times the square root of 2. And if you divide that by 2, you're just going to get square root of 2. So you're just going to get that right there. Okay? So what happens? Here we have square root of 2 is not as big as 2. So here's 2 plus the square root of 2. And here's 2 minus the square root of 2. Just for sake of reference, there's 0 right there. Okay? 2 would obviously lie right in between these two things. So let's stick something on all sides. If you stick in a really huge positive number here, like a billion, that's going to be positive, positive, everything is going to be positive. Stick in a nice number between these two, such as 2, and what do we get? 4 minus 8 is negative 4, plus 2 is a negative 2. So it's negative there. And if you stick in a number over here, such as 0, you're going to be back to positive again. Okay? So it's concave up here, down here, and up there. Okay, so I've got everything except for a place to graph it. Let's see. I've got this information here. Let me get rid of this just to give me a place to graph it. Okay, and here's the graph. Most of the action is over here. So let's see what happens. Here we have 0, it goes through 0. Here we have 2, it increases until it gets to 2. And then here you have 2 minus the square root of 2. And here you have 2 plus the square root of 2. Okay? So until you get to 0, it is decreasing and concave up. So it must look like this. Decreasing and concave up. Once you pass 0, it's still concave up, but it's now increasing. It's increasing until I get to 2. So it's increasing, concave up. Once I pass this point, it becomes concave down. Now I'm at 2, so now I start decreasing. It's still concave down until I get to 2 plus the square root of 2, and then it becomes concave up. Oh, what a nice problem. Isn't that great? Beautiful. So there it is right there. Okay, so that's a nice one, and I'm glad we did that one. Okay, here's the last one I want to do. Just one more involving the Fundamental Theorem of Calculus. Okay, so we're going to need a graph to start with here. Let's start with this one right here. Let's say we start with one that starts at the point 0, 3, goes down to 3, 0, continues down with the same line to 4, negative 1, and then climbs back up to 6, 0, and let's say continues climbing to the point 8, 1. Okay, so there's the function, and this is small f right here. And as we've done before, we're going to let capital F be equal to the integral of small f from 0 to x. Okay, so this graph right here is small f, and capital F is the integral. So let's think about what capital F looks like. Okay, first, capital F of 0 is the amount of area you've accumulated at point 0. That's going to be 0. Where is capital F positive? Think about that. You've gained a whole bunch of stuff by the time you've gotten to here, right? You've gained all this area. This is all positive area. What is that? That's the total area there is 3 by 3 times 1/2 is going to be 9 halves. Is that area right there? And then as you continue here, everything is negative that you're getting as a contribution. And what's the total area of that? It's going to be 3 by 1, which is 3 times 1 is 3 times 1/2 is going to be a negative 3 halves. That's the contribution of that. And then finally here you have 2 by 1, which is 2 times 1/2, which is 1. So that total area is 1. So the point is, by the time you've climbed from here to here, you're already at 9 halves. By the time you get to here, you're at, well, I tell you what, let's just do it like this. Let's just do it like this. Let's just say, what is f of 0? F of 0 is equal to 0. F of 3 is equal to what? You've got this contribution right here, so that's going to be 9 halves. F of 6, by the time you've gotten here, you've got this contribution plus this contribution, which is going to be 9 halves minus 3 halves is 6 halves. 6 halves is the same as 3. And then finally, by the time you get to here, you've picked up another 1, so it's going to be f of 8 is going to be 4. Okay, those are the values of the function. How about the value of the derivative at these points? Well, recall that the derivative of capital F is just the value of small f, right? The rate at which this area function grows depends on the height of your small f. So, what's the value of small f at these points? the value of small f at 0 is 3. The value of small f at 3 is 0. The value of small f at 6 is 0. And the value of small f at 8 is 1. So the rate at which capital F is growing at those points is right there. Okay? What about the second derivative of f at these points? Well, the second derivative of capital F is equal to the derivative of this is the derivative of that. So that's the derivative of small f. What's the derivative of small f at this point? Well, this is a line that has slope of -1. We can think of continuing it on there just a tiny little bit if you want to. And so at this point right here, the slope would be -1. At 3, the slope of this continues to be -1. Because you've kept going down. Here, what are you doing? You're going up 1 and over 2, so the slope here is a 1/2. So the slope at 6 is 1/2, and the slope here at 8 is also 1/2. See that? So you have that. Where is f increasing? F is increasing whenever the derivative is positive. So capital F is increasing on the interval from 0 to 3, and on the interval where small f is positive from 6 to 8. That's where you're gaining land, right? Remember that analogy? Gaining land. Where is f concave up? It's concave up whenever the second derivative of f is positive. But the second derivative of f is equal to the first derivative of small f, and the first derivative of small f is positive from where? From 4 to 8. Okay? So if we put all this together, what do we have? We have ourselves, raise that up just a little bit. Okay? We have ourselves a function that starts at 0. It's increasing in concave up until you get to 3. There you are at 3. It continues concave up, but at 3 it starts, it's increasing in concave up until you get to, oh no, wait a second, I'm sorry, it's increasing and concave down. It's concave down. It's concave down until you get to 3. So there it's increasing and concave down until you get to 3. Once you pass 3, it starts decreasing all the way to 6. So it's decreasing. It's still concave down until you get to 4. See that? At 4, it starts becoming concave up. So now it becomes concave up. Okay, until you get to 6. Once you get to 6, it starts increasing again, and it continues being concave up all until you get to 8. So it starts going like that. Okay? And to find the values there, you can actually stick in those. But that's roughly what it looks like. It looks like the largest value of the function is going to occur at 3. So this one right here at 8 is going to be increasing. Maybe that's 8 right there, where it increases, but it doesn't get as high as it did right there. So there you go. So nice problem. Again, it reviews derivatives, second derivatives, concavity, increasing. It reviews the central limit theorem. I'm sorry, central limit theorem, the fundamental theorem of calculus, and which together with the central limit theorem are probably the two most important theorems in all of mathematics. Central limit theorem belongs to statistics, but recall we talked about that one when we graphed e to the negative x squared. So So all these great branches of mathematics are all tied together. So anyway, well, thank you if you took the whole course with me. I appreciate your resolve and your dedication and hope that you found it both enjoyable and a good learning experience. So very good. Thank you very much.